Hello everyone. For this tutorial video, I'd like to talk about what a separable differential equation is and how it comes in a very specific format, so you can use basically the same steps to solve each one regardless of how exactly it looks. A separable differential equation is written explicitly in the format y derivative equals function of x times function 2 or g of y. Because of this, any g of y that gives us a value of 0 would logically tell us that y derivative is 0, so we can single out constant solutions right away from that method. But then we must also get more general solutions by separating terms of y and terms of x on different sides, integrating both sides of the equation, solve the equation for y explicitly using techniques from algebra, and plugging in the appropriate specific values for x and y if you are given an initial condition. But only if you are given an initial condition. If you are not, then you cannot do that step. An example problem is this differential equation, where you are asked to find a general solution rather than a specific solution for a certain x and y value. We first identify our function of x and our g of y. See, when y equals negative 2/3, g of y equals 0, so that is a constant solution. And then divide the left-hand side by 3y plus 2 in order to get terms of y and terms of x on separate sides. And now we integrate both sides to try to figure out a specific value of y. We see the right-hand side integrates perfectly normally, but the left-hand side is more difficult to deal with because we're integrating with respect to change in x. So what we would have to do to solve this problem is use the substitution rule, where we substitute in the g of y for the u, so 3y plus 2 equals u. So this would logically mean the differential of u equals 3 times the change in y times the change in x. So we'd use this substitution to simplify the left-hand integral. And then we would plug back in 3y plus 2 for u after we are done, like we would normally do for a u substitution problem. And now we would first multiply both sides by 3 to get the ln isolated by itself. And then we would try to get rid of the ln to more easily get y by itself, which we would do by raising e to the power on both sides. We can next simplify the right-hand side using properties of exponents, and assume, to make our life simpler, that e raised to the power of a constant is a constant number, which is true logically. Get rid of the absolute value bars by making two separate equations, one normal and one with a negative sign tacked on the right hand. And then finally, use simple algebra techniques to get y all by itself, and we conclude that y must logically be this exact function. If we're given a more tricky problem that also gives an initial condition like this, we would first get terms of x and y on different sides per usual, and then take the integral of both sides, again as we would usually do in a problem like this. But we see the left-hand side integral is a lot more messy and cannot be done with u substitution right away, so we'd use the method of partial fractions. But the right-hand side still is relatively easy to evaluate, given that you memorized basic integral formulas. We next multiply both sides by 4 to get rid of the 1/4 on the left-hand side, and also use properties of logarithms to get the left-hand side in terms of one logarithm rather than two separate ones, and then raise e to the power of both sides to get rid of the logarithm on the left-hand side. And see that another thing that is messy about this problem compared to the previous one is that we have y in the denominator as well as the numerator, so we will have to do more steps to get y by itself. We would first have to take away the absolute value bars, but then we would multiply the right-hand side by the denominator of the left-hand side, and we can expand it algebraically using basic distribution, so that we can more easily get terms of y and terms of x on different sides, which we want to do in order to get y easily by itself. And we conclude when all is said and done, y equals this exact value, which is obviously very complicated and messy, but it is the exact value from all the steps. Although we have just found the general solution or function, we have to remember in this problem we were given an initial condition as well, so we now have to solve for the constant in terms of an exact value. If we remember from one part of our solution, we got this thing. So you'd simply plug in -1 for y and 0 for x, and manipulate everything to get an exact value for the constant. And when all is said and done, we should logically conclude that the constant has a value of -3. Before I talk about how to solve the last important type of differential equation, first-order linear differential equations, in the next tutorial video, I like to talk about a real-world calculation you can do with a separable differential equation, which is Isaac Newton's law of cooling for conduction. In particular, the formula is stated as change in temperature over change in time equals thermal conductivity, written K, times change in temperature. And although this formula is not what you will see for the actual conduction formula in physics classes, because it involves other factors such as cross-sectional area and thickness of the region that this formula alone does not explain, it was a good approximation for its time, so we can practice problem solving it in order to predict approximate temperatures at specific times. For example, if we were told in this problem that the room temperature is exactly 75 degrees Fahrenheit, and the initial temperature of the pizza or the temperature of the oven it was cooking in is 350 degrees Fahrenheit, and also told the pizza is 340 degrees Fahrenheit after 5 minutes, we can calculate the exact amount of time it would take to cool down to, say, 300 degrees Fahrenheit for argument's sake, by completing this differential equation. In particular, we would write the formula as given above, but plug in the value of 75 where appropriate, and also see that we are given an initial value where the temperature at 0 minutes is 350. So we would get terms of temperature on one side, and everything else on the other side, as appropriate. Take the integral of both sides. Use u substitution for the left-hand side, but the normal integral formula for the right-hand side, where we remember the integral of a constant is a linear function. And then we would attempt to solve for the temperature by first getting rid of the ln, by raising both sides e to the power of whatever it is. Get rid of the absolute value bars, and finally add 75 to both sides. And then, since we are given an initial value of 350 for 0, we would plug in 0 for time and 350 for temperature. So we should be able to logically conclude, after we do the arithmetic, the constant equals 275. We can next get an exact value of the thermal conductivity K by utilizing the fact that the pizza is 340 degrees Fahrenheit after 5 minutes, so plugging in 5 for minutes and 340 for temperature. So now, after we do some algebra, we get e to the power of 5 times k equals 53 over 55. So now we take the ln of both sides to try to get k by itself more easily. And then finally, divide the right hand side by 5, and conclude that is our exact value for k. So now that we know exact values for the constant as well as the thermal conductivity, we would plug in 300 for the temperature, and then do basic algebra techniques to find a value for t. We first subtract 75 from both sides, get it in terms of e alone on one side, take the ln of both sides to get rid of the e, and then finally divide both sides by the thermal conductivity we found to get t by itself, and conclude that this is the exact amount of time it will take. Now that I've explained the problem-solving techniques for separable differential equations, as well as some real-life applications of them, I can talk about how to solve the most sophisticated 1D differential equation, which is called the first-order linear differential equation because of how it is organized in a similar manner to a linear function from normal algebra classes. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.